Okay, we're going to wrap up this chapter, roll into the next one. We're still talking about kind of thermodynamics here, and really delta G. And at this point, we've seen a few different sort of delta G equations. We have delta G is equal to delta H minus T delta S. Clearly, if you have either of those sort of values given to you, H and S, this would be probably your choice to use. You do want to watch units as we talked about. Again, typically kilojoules there and joules there. We also can do our delta G of formation, which is basically delta G of our products minus the delta G of our reactants. We also saw a delta G equation for sort of non-standard conditions. Delta G equals delta G naught plus RT natural log of Q. This guy right here is what's above. R is our gas constant with energy. T is our temperature in Kelvin. And Q is our reaction quotient, which again is our products divided by reactants. We calculate obviously the same way as we calculate Q or K. And again, in this case, we would use this equation if there is something that is sort of not under standard conditions. Remember, typically standard condition means if you're doing anything with pressures, they all should be 1 atmosphere. If you're doing anything with sort of concentrations, they all should be 1 molar. Lastly, we saw the relationship between delta G and K, and we could get that by at equilibrium, delta G equals 0 and Q would equal K. And that gets us to this sort of fourth delta G equation here that relates the equilibrium constant. So again, we have a few different sort of delta G equations, and which one to use, as we talked about last time, probably based on the information sort of given to you in the problem. But we can use delta G to help us decide whether or not our reaction is going to be spontaneous or non-spontaneous the way it's written. Again, if delta G is negative, then it should be a spontaneous reaction the way it's written. And if it's a positive value, it should be a non-spontaneous reaction. And again, all the normal things should agree with each other. So again, if you have a spontaneous reaction with a negative delta G, that means you should have probably products being made. And because you're having products being made, if you're looking at an equilibrium constant, you probably should then have a large value of K because of that. And vice versa, if you got a kind of positive value of G, that would mean the reaction is really non-spontaneous the way it's written. It's going to pretty much hang out on the reactant side, and that means when you reach equilibrium, you probably mainly have reactants, and that should correlate to a smaller value of K. Any questions on any of that stuff there? All right, so I think we just got a couple more examples to go here, so let's do those. Calculate the delta G naught for the following reaction if the KSP is 1.7 times 10 to the minus 6. So give it a go there, see what you come up with. Okay, so let's take a look at it. So obviously here we're looking for delta G. We're given a K. So our delta G naught is minus RT natural log of K. Would seem like a logical one to use here. We pretty much got everything on this side, so we just need to plug it in. So delta G naught is equal to minus RR 8.314. Our temperature, we do need to convert into Kelvin, so add a 273 to it. Gives us a 298. Natural log of 1.7 times 10 to the minus 6. So we put all that in there. We end up with about 32,914 joules, or if we wanted in kilojoules, about 32.9 kilojoules here as our delta G. This is a positive delta G, which means this reaction is non-spontaneous the way it's written. We would expect mainly reactants, and that kind of goes with our small value of K that we also have here. So again, those things should sort of agree with each other. Any questions on that one there? All right, let's take a look at one last one here, I think. Yeah. Truthfully, typically speaking, delta G and delta H are usually given in kilojoules, and S is usually given in joules. But technically speaking, if it doesn't specify any of those units are okay. Yeah. Because, yeah. Say again? It is, yeah. So K is equilibrium constant, so it doesn't really matter what type of equilibrium constant it is. So in this case, happens to be a KSP. Yeah. Other questions? Okay. All right, so let's try this one then. The delta G naught for this reaction is 2.6 kilojoules per mole at 25 degrees. In one experiment, the initial pressures for H2 4.26, I2 0.024, and HI 0.23. What is the delta G for this reaction, and predict which way it will go? Okay, so let's take a look at this one here. We're looking for a delta G. We do have a delta G not given to us. So clearly this is the one where we need to use this equation here that has them both in it. A reminder that it is a plus here. This delta G naught is under standard conditions. This is a sort of non-standard conditions, the second one there. And it was given to us under standard conditions. If it wasn't, you would need to go to the table and do products minus reactants to calculate it. So we do have that. Why this is under non-standard conditions is as we look at the pressures here, these are not all 1 atmosphere. Actually, none of them are. And that is what makes it sort of non-standard conditions is the pressures that we're dealing with at this point. So we do kind of have most of the things over here. We do need to calculate Q. Q, again, is going to be our products divided by our reactants. And again, we got to square it because it's coefficient. And in this particular case, since we're actually doing pressures, we'll need the pressure squared of HI, pressure of H2, and the pressure of I2. So putting our numbers in here, HI is 0.23. We got to square it. Divided by our H2, 4.26, and our 0.024 in this case. That's going to get us here. Looks like 0.5174 as our Q. Here we will put in everything. Our delta G is equal to our delta G naught, which was given to us, 2.6. Once again, I'm going to multiply by 1,000 to convert that into joules. Again, the reason I really need to do that is, again, my R value here is in joules. So again, if you don't do that conversion, you're going to be off. Somewhere I should have said 25 degrees, so we'll go with 298 on the temperature there. And our natural log here, what we just calculated there, 0.5174. All right, so we'll clean up the right-hand side here, the plus, so natural log that times 298 times 8.314. That is going to get me a plus minus 1632.5 joules plus my 2.6 times 1,000 plus that number. Going to yield me here 967 joules as my delta G, or it would actually be 0.967 kilojoules if you left it in kilojoules in this particular case. First off, any question on the calculation there? This is a positive value for delta G, which means this reaction is non-spontaneous the way it's written, and we would expect reactants at this point. Any questions on that one there? All right, so that wraps up chapter 16 in thermodynamics, part 2 here. All right, we're going to then go off to next chapter. Okay, the next chapter we're going to talk about is 17 in electrochemistry. So really the main part of this chapter deals with galvanic cells and electrochemistry like that. We are up here up front going to go over redox reactions, oxidation, reduction, balancing redox reactions, just to make sure everybody's on the same page, depending on who maybe you had for the first semester, maybe did more or less of this. So that way, hopefully, we'll be on the same page when we get to the real part of sort of this chapter here. So the first thing we're going to really talk about is redox sort of reactions here. And redox reactions involve oxidation and reduction reactions that occur. So in an electrical chemical process, like we're going to talk about in this chapter, it deals with an oxidation reduction reaction. Those always occur together. So if there is somebody being oxidized, there is going to be somebody that is going to get reduced in the same sort of reaction. The energy released by these reactions can be converted into electricity and used to do some type of work. So as the electrons get transferred, they could go out over a wire and basically power a device. So when we look at a reaction such as this, which is magnesium plus oxygen, excuse me, making magnesium oxide here. If we look at the oxidation numbers here, this is 0, this is 0. And then on the right-hand side, the magnesium has a +2 charge, and the oxygen has a -2 charge. Remember that anything sort of in its natural state that is uncombined does not have a charge. And when we talk about oxidation, one of the definitions of oxidation is to lose an electron, and reduction means to gain an electron. And once again, when you lose electrons, you do become more positive, and when you gain electrons, you become more negative. So if you're not really sure, an easy way to figure out what is being oxidized and what is being reduced is to just make a simple number line. And as you go through oxidation and you lose electrons, you have more protons than electrons. And that means that if you look at the oxidation state from the left-hand side of the arrow to the right-hand side of the arrow, you'll be moving in this direction on the number line, the more positive direction. And that thing is going through oxidation. When you gain electrons, you obviously gain more electrons than protons. You'll actually see the oxidation number as you go from left to right, heading towards the left there, towards the negative side. And that is something that is going through reduction. Some people like to remember it. Leo the lion goes grr, right? Loss of electrons, oxidation, gaining of electrons, reduction. People nowadays are fond of the oil rig. Oxidizing is losing, reducing is gaining. So, you can put Leo the lion on the oil rig. He goes grr. You don't have to choose. But that's a really easy way to sort of figure out what is going on. So when we do look at this, what's happening here, if we look at the magnesium, how this works is pretty straightforward. Magnesium is starting at 0 on the left-hand side. On the right-hand side is becoming +2. It is definitely moving in the positive direction, which means in this case, magnesium is going through the oxidation. By default, the O2 would be going through reduction, but you could also see that with the O2. This is magnesium. O2 starting at 0 and ending at -2, becoming more negative, heading towards a negative direction, and is going through reduction. So ultimately what is happening in this case is the magnesium is transferring electrons from itself to the oxygens, and it's at that point they do gain charges. We could write, as you probably are familiar with, half reactions when we look at redox reactions. Half reactions tell you half of the story that's going on. One half reaction is an oxidation half reaction. We know it's an oxidation half reaction because the electrons here are found on the product side of the arrow. Like the magnesium here is losing those electrons. Each magnesium will lose two, and that's why we're up to 4 electrons here, since we have 2 magnesiums. Over here is the reduction half reaction, and that is where oxygen is gaining the 4 electrons. And we think of a reduction half reaction as the electrons should be on the reactant side, like they're being gained. They're obviously called half reactions because when you add them together, they should add back up to the overall reaction that is taking place. By the way, before you could ever add 2 half reactions together, one of the things you do need to make sure of is that you have the same number of electrons in each half reaction. The electrons should completely cancel out. And that means that sometimes, as you may be familiar with, you may have to multiply 1 half reaction by a number, or you may have to multiply both half reactions by a number to get the same number of electrons in each. In this case, electrons cancel. Everything on the left stays on the left. Everything on the right stays on the right. These two ions will actually come together to make two of those guys. And that gives us our overall reaction of what is going on in this particular case. This is also what we would expect to happen since this is a metal and a non-metal. Metals typically always lose electrons, right? Non-metals always gain electrons. And that should always be the situation of how early an ionic compound is formed. Any questions on that there? By the way, redox reactions is a big class of reactions where you have things like single replacement reactions, synthesis reactions, decomposition reactions, combustion reactions fall underneath the redox category. It's one of the 3 reasons why a reaction takes place, which is a transfer of an electron, is one of the 3 reasons why a reaction takes place, and that's what's happening in redox reactions. The other 2 reasons, formation of a solid or formation of water, is what happens in double displacement reactions. And those are the 3 reasons why pretty much any reaction takes place. Now, in addition to that, we could look at this one here. If we look at what is going on here, we have calcium on the left, which has an oxidation state of 0. Oxygen, oxidation state of 0. When those two guys come together, our calcium can get a +2 and a -2. So once again, if we roll to our sort of number line here, oxygen or calcium starting at 0, ending at +2, becoming more positive. So once again here, as we would expect, this is going through oxidation. The O2 again starting at 0, ending at -2, again going through reduction. By the way, what is being oxidized and what is being reduced should always be found on the reactant side of the arrow, not the product side of the arrow in this case. And we again have our half reactions here, and our electrons going to completely cancel out and give us our overall reaction. Now, in addition to what is being oxidized and what is being reduced, sometimes you are asked about the oxidizing agent and the reducing agent. And those are different things than what is being oxidized and what is being reduced. The oxidizing agent is the substance that gets reduced, and the reducing agent is the substance that gets oxidized. They are called that because they basically cause the opposite effect to occur in the other species. So when we look at calcium in this example, which is going through oxidation, it would be our reducing agent because when it loses those electrons, it's going to allow somebody else to gain electrons and go through reduction. While O2 is our thing going through reduction, it would be our oxidizing agent. In order for it to gain electrons, it has to cause somebody to lose electrons and go through oxidation. So again, if you're asked what is a reducing agent or oxidizing agent, that is different question than what is being oxidized and what is being reduced. Any questions on that there? Now, when we talk about oxidation and reduction, for the most part in general chemistry, the definitions that we use do involve electrons. There are other definitions of oxidation and reduction. Oxidation can mean, as I talked about a second ago, obviously losing electrons. It could also mean that you gain oxygen as you go from reactants to products. So some species gains oxygen as it goes from the left-hand side to the right-hand side, or it loses hydrogen as it goes from reactants to products. So those are three definitions of something being oxidized or going through oxidation. Reduction is pretty much the opposite. So reduction, again, gaining electrons, losing oxygen as you go from reactants to products, and gaining hydrogen as you go from reactants to products. So these are three definitions for both oxidation and reduction. I would say in most general chemistry classes, we usually focus more on the losing and gaining of electrons. When you go to organic chemistry, you actually focus a lot more on the gaining oxygen or losing hydrogen or gaining hydrogen. Again, in organic chemistry, there's a lot less metals involved, a lot more non-metals happening. So it's much easier sometimes to just follow whether or not something sort of gained oxygen or lost oxygen, or gained hydrogen or lost hydrogen along the way. But here in general chemistry, oftentimes we look more at the electrons being gained or lost. Questions on that there? And here we go. We can see our carbon in this case is the reducing agent as it brings about the loss of oxygen. Again, in this situation, if we look at the carbon here on the left-hand side versus the right-hand side, so we can see from here to here, it has gained oxygen, which means it is going through oxidation. We also see that the tin has lost oxygen as you go this way, which means it's going through reduction in this particular case. So again, by looking at the oxygen gaining or losing, you could actually figure out what is being oxidized and what is being reduced. In this particular case, since we actually did still have the tin involved, we could look at the tin and see what's happening with it. Oxygen here is -2. There's two of them. It's -4. So that's a tin 4 on the left-hand side, and that's a tin with no oxidation state on the right. So if you just look at the tin, it starts at +4, ends at 0, and is definitely going through reduction in this case, as is becoming more negative. Remember that all you have to do basically is figure out one thing, who's being oxidized or who's being reduced, and the opposite thing is happening to the other substance. Oxygen will not always be -2, but most of the time it is. We're going to talk about it in just a second, I think. But the answer is peroxide. What is peroxide? Any questions on that? All right. So let's talk about how to identify oxidation numbers, or sometimes referred to as oxidation states. And again, a reminder that when you talk about oxidation numbers or oxidation states, it is not always the charge that you think an element will have in its ionic compound, especially if they are sharing electrons through covalent bonding. Things that you normally think about that may have, for example, a -1 charge may actually be a positive oxidation state or oxidation number. So in covalent bonding, because of sharing of electrons and who they're sharing it with, can cause different oxidation numbers. So the rules for identifying and counting oxidation numbers: any element that is basically by itself free, uncombined, will have an oxidation state of 0. So anybody from the periodic table that's by itself, O2, H2, how it naturally comes, their oxidation states will be 0. If you have a monoatomic ion, the oxidation state will equal the charge of the ion. So if you have an iron 3 ion there, the +3 is the oxidation state. If you have a lithium ion, it's +1. Oxygen, as we talked about here, is a really good place to start. In a lot of cases, it is going to be -2. It may not always be -2, but that's usually a good place to start. The oxidation number of oxygen is usually -2. The exception is, though, if it is peroxide, which is this guy right here, polyatomic ion, it actually will be -1 versus -1. I would say probably in most cases, you could probably safely assume that the oxygen is probably oxygen. But it is possible it could be peroxide. If you had like H2O2, that is hydrogen peroxide. And here this would be -1 and +1 for the oxidation states rather than -2 there for the oxygen. The oxidation state of hydrogen is +1, except if it is bonded to a metal in a binary compound, then it's going to be -1, like if you have LiH, that is +1 and -1 for hydrogen. In this case, if it comes after a metal. Everybody in group 1 will have this +1 as his oxidation state. Everybody in group 2 will be +2. Fluorine is -1. When you add up all the oxidation numbers, they do need to equal the charge on the molecule or ion. So if the molecule is 0, then everybody needs to add up to 0. If it is -2, then everybody needs to add up to -2. So when we look at peroxide is -1 because it's peroxide is not really oxygen. No, it's not O2. It's actually peroxide. Yeah. So if we look at HCO3 minus, this is bicarbonate, and I would always recommend that if you have kind of like a 3-pack of elements like this, you usually want to go with the oxygen first if it's there, and kind of go right, go left, and would save the person there in the center for the end. So here we would look at -2 for the oxygen. There are 3 of them, which gives me a -6. Hydrogen here is +1, gives me a +1. This entire thing here has a -1 charge. And that means that all my oxidation states need to equal to that. So that's -6 and +1 is -5. That means here the carbon is going with a +4 for its oxidation state. That will give me a -1 left over. Now, if you're going to give the answers for oxidation numbers or states, hydrogens would be +1, carbon would be +4, and oxygen here would be -2, not -6. So sometimes people write like the grand total of all of them together. So when you're stating an oxidation number or state is just for one of them by itself. And you should also include the sign, both positive and negative, when you're writing oxidation numbers. So you shouldn't just write 4. So you should write +4 or something like that as well. Any questions on that there? All right, so why don't you give it a go here for each of these. I give the oxidation numbers for each. So oxygen is a good place to start, -2. And lithium, which is group 1, will have its normal sort of charge and oxidation state. So lithium would be +1. And again, here oxygen would be -2. Coming over to our PF3, fluorine is going to be -1. There are 3 of them, gives me a -3. To balance it out here, the phosphorus would have a +3. So the oxidation state on phosphorus is +3. And fluorine here, -1 in this case. So once again, this is a case where phosphorus is sharing electrons in this case. It is covalently bonded, and that is why it's not the normal -3 that you associate with phosphorus, because that's an ionic compound. In this case, phosphorus, because it's sharing electrons with a very electronegative element like fluorine, all the electrons are going to be sucked away from the phosphorus and going to make, in this case, phosphorus more and more positive in this sort of sharing of electrons than we normally think of it in an ionic compound where it's negative. Here, if we look at nitric acid, -2 for the oxygen, That's a -6 going to the hydrogen next, +1. And in this case, nitric acid is no charge overall. So here the nitrogen is going to be rocking a +5 oxidation state. And again, it's a similar reason why the nitrogen ends up with a more positive oxidation number than the more negative one we see in an ionic compound. Again, if you quickly sketch it, looks something like this. And again, we have a polar bond, more polar oxygens, more electronegative oxygens, going to kind of suck the electrons out of the nitrogen. And that's again going to make this guy become more and more positive because of the unequal sharing of electrons in this case, and end up with a positive oxidation number. Lastly here, dichromate, -2 for the oxygen, -14. Overall, this thing is equal to -2. We actually have 2 chromiums in this case, and that means each of the chromiums would actually have to be +6. That gives me a +12 and a -14, so -2 overall. So the chromium in this case is +6. Oxygen is -2. Any questions on how to assign oxidation numbers or states? Really important in this chapter to be able to do that so you understand what is going on, who is being oxidized and who is being reduced, especially when we get into galvanic cells. Really important. Any questions? Okay. Okay, the next thing we're going to talk about is balancing redox reactions in acidic or basic solutions. And again, in just kind of regular solutions, you just have 2 half reactions. Really, the only thing you have to worry about is just to make sure that you have the same number of electrons in each half reaction before you add them together. Here it is a little bit more complicated, so we're going to go through the steps here to balance it in acidic and our basic conditions. We're going to start with acidic conditions first. And what we got here? We go here, Fe2 plus some dichromate, iron 3, and chromium. All right, so the first thing we're going to talk about is balancing in acidic conditions, and then we'll talk about how to turn it into basic conditions, which is probably the easiest way. The first thing you might want to think about, though, is sort of what is happening, who's being oxidized, who's being reduced. So when we look at our oxidation numbers here, the iron has a +2. We just did this guy a second ago. The chromium is a +6. The iron over here is a +3, and the chromium is a +3 in this case as well. So if you're not sure, you take your number line here and you look at the iron. The iron on the left there is +2, and on the right it is +3, so it is moving in a more positive direction. That means the iron here is going through oxidation. By default, it's the dichromate here going through reduction, and we can see that as well. The dichromate or chromium starts at +6, which is over here, and ends at +3, which is going in the more negative direction and going through reduction. That would also mean here that the iron 2 is our reducing agent and the dichromate is our oxidizing agent in this particular case. Any questions on how to identify all that stuff there? At this point, the next thing you want to do is basically just break this equation into its 2 half reactions. To do that, you basically just take element to element, so whatever elements are the same, you're going to put them together. So in this case, we have an iron 2 that's going to an iron 3. And on the second one, we have a dichromate here going to a chromium 3. So once you've done that and you split it off into its half reactions, since we've already identified what's going on, we know that's our oxidation half reaction, and that is our reduction half reaction. The next thing you want to do is balance all the elements except for hydrogen and oxygen. So we balance them just like a normal equation. We use a coefficient. In the top equation here, we have 1 iron on each side. On the bottom equation, we have 2 chromiums on the left and only 1 on the right. So we will need to put a 2 in front of the chromium here on the bottom. Now that we have balanced all the other elements besides hydrogen and oxygen, we're going to balance oxygen next. And we balance oxygen by adding water. So we add water to whichever side needs the oxygen. But because we're adding water to balance out the oxygen, to the opposite side, we would need to add 2 H pluses for every water that we add. Otherwise, we're going to be short hydrogens by adding that. So in the top equation, there's no oxygen on either side, so we don't have to worry about it. Bottom equation, there's 7 oxygens on the left, none on the right. That means here we need 7 waters. And once again, because I added 7 waters, I need to add 14 H pluses to the left-hand side. That way I am not short in terms of hydrogen. So water to whichever side needs the oxygen, appropriate number of H pluses to the opposite side to balance out the hydrogen that you added for the water. Any questions up to that point? Once you've balanced all the elements and once you've added water to balance out the oxygens, by the way, if you're ever short hydrogen to begin with, you could just add H pluses to the opposite side just off the bat there and kind of balance it out that way as well. We want to balance out the sides, balance out the charge by adding electrons. So we want to make sure that the overall charge in each half reaction on each side of the arrow equal each other. They do not have to equal 0, they just need to equal the exact same number on each side. So for example here, overall on the left-hand side, that's a +2. Overall on the right-hand side, that is a +3. So the right-hand side here would need an electron because that's going to give me a -1 and a +3. Gives me a +2 on both sides of the arrow now, so I am balanced. When I look at the bottom one here, this guy is going to contribute +14. This entire thing is going to contribute -2. That gives me a grand total of +12 happening on the left-hand side of the arrow. On the right-hand side of the arrow, I got a +6 contributing there and a 0. I got a +6. So in this case, we would actually need to add 6 electrons to the left-hand side of the bottom arrow reaction. And that +6 is going to give me 6 negatives. Actually, you go that way, -6. And that will give me a +6 over on the left to match the +6 on the right. Any questions on that? Now, understanding which one is your oxidation and reduction reaction up front can be really helpful because you'll know if you added electrons to the correct side. This is the oxidation half reaction, and we added electrons to the right-hand side, and that is correct, like they're being given off. This is the reduction half reaction, and we added electrons on the left-hand side, so that is also correct as well. Once again, you should never add electrons to the same side because you're definitely doing something incorrect at this point. We are ready at this point to add these half reactions together. But once again, before we could add them together, we do need to make sure we have the same number of electrons in each of the half reactions. And if we look at it here, we actually have 1 electron in the top reaction and 6 electrons in the bottom reaction. So that's going to require us to take the top half reaction and multiply it by 6. And I'm just going to rewrite it underneath the bottom reaction. So that'll give me 6 Fe2 plus goes to 6 Fe3 plus and 6 electrons. Now I am ready to add these together. Anything that's on opposite sides of the arrow can completely cancel or reduce down. So here, definitely for sure what should completely cancel are electrons. So the electrons should definitely completely cancel. At that point, I think that's everything. That's going to leave me here on the left-hand side 14 H pluses plus Cr2O72 minus plus 6 of the iron 2. Going to my right-hand side here, 2 of the Cr3 plus 7 waters and 6 of the Fe3 plus. If I did everything correct at this point, this should be the balanced equation in acidic conditions. Now, what does that mean if I did everything correct? These equations should be balanced in two ways. They should be balanced like a normal chemical equation, which means you should have the same number of elements on each side. So if we look at it there, we have 14 hydrogens on the left, 14 on the right. We have 2 chromiums on the left, 2 chromiums on the right. We have 7 oxygens on the left, 7 oxygens on the right, 6 irons on the left, and 6 irons on the right. So it is balanced like a regular equation. Secondly, the overall charge in this reaction should be the same on both sides of the arrow. Once again, it does not have to be 0, but it does need to be the same charge. This guy's contributing plus 14. This is contributing minus 2 and plus 12. That gives me a plus 26 less 2, a plus 24 overall on the left-hand side. That is a plus 8, plus 6. This is a 0, and that is a plus 18. 18 and plus 6 is a plus 24. So again, this would be the balanced equation in acidic conditions, both balanced like a normal equation and also overall charge. First off, any questions on that there? By the way, how do I know this is balanced in acidic conditions? I know it's balanced in acidic conditions because that says H plus right there, yeah. So definitely balanced in acidic conditions would be a good little key that is. Now, how do you balance these guys in basic conditions? There are a couple ways you could do it, but probably the easiest way to do it is what we just did, which is go ahead and balance the equation in acidic conditions. And at the end, you could turn it into basic conditions with relatively little work. You could also do it a different way, but it's a lot more canceling out and conversion. So this would probably be the best move. So if we wanted to turn this into basic conditions, I'm just going to recopy the equation here, 14H plus Cr2O72 minus plus 6Fe2 plus 2Cr3 plus 7 waters and 6 of the iron 3s. All right, so if we want to turn this into basic conditions, we're actually going to add hydroxide to both sides. We're going to do a little OH minus both sides. How much OH minus should you add? It should be equal to the H plus. So in this case, we have 14 H pluses. That means this side gets 14 OH minuses, and this side gets 14 OH minuses. The side that has OH minus and H plus, this will come together to make 14 waters in this case. And typically speaking, you can reduce it down. 7 waters on the right will reduce this down to 7 waters on the left, plus my dichromate, plus my 6 iron goes to my right-hand side here. My 2 Cr3 plus, my 6 iron 3 plus, and my 14 OH minus in this case. So at this point, this should be balanced in basic conditions. Again, it should still be balanced the same way. I have 14 hydrogens there, 14 there, 7 oxygens there, plus 7 more is 14. So 14 oxygens, 2 chromiums, 6 iron. Overall charge on the left is -2 and +12. So that is a +10. Over on the right-hand side, that's a +6 from this guy. That's a +18 and a -14 here. So -14 and 18 is +4. +4 and +6 is +10 when it's all said and done. So it is balanced on both sides, normal equation and also charge. Much like the other one, I know this is actually balanced in basic conditions because I see OH minus in my balanced equation. So I know it is balanced in basic conditions. Any questions on how to balance that there? Hopefully for most review, I hope. All right. So just try one more just to make sure maybe we're all through this here. All right, why don't you try this one here? I minus plus MnO4 minus goes to I2 plus MnO2. Balance this guy in basic conditions. So give it a go. See what you come up with. This is going to be -1 for the oxidation state. -2 for the oxygen. There's 4. It's -8 overall. -1. That means that's a +7 for the Mn in this case. I2 would be 0. -2 for the oxygen here. -4 overall 0. So that is a +4 in this situation. That means if you're not sure, just roll to the number line here. The I minus starts at -1 and ends at 0. So it's actually moving in the positive direction here. So that is being oxidized. The Mn is starting out like +7 over here and ending at +4, which is moving in the negative direction and is being reduced in this case. That would mean that this is my reducing agent, and that right there is my oxidizing agent. Any questions on any of that there? All right, going to split it off I's with I's, I think. And MN's with MN's seem like a good move. And this is my oxidizing agent reaction, half reaction, and my reduction half reaction. All right, so balancing everything outside of hydrogen and oxygen, we do need to put a 2 here in front of the I, and that's about it. We then can move to oxygen. Nothing going on in the first half reaction. Second one, we do need 2 waters. And again, because I added 2 waters to the right-hand side, I do need to add 4 H pluses there to the left to balance out the hydrogens. At this point, I have now balanced everything, oxygen, hydrogen, and all other elements. For now, we're looking to add electrons. Overall charge here is -2 and 0. That means right-hand side here needs a couple of electrons, and that will get me -2 on the right to match the -2 on the left. On the bottom here, that's going to be a +4. That entire thing's a -1. So that's a +3 overall. That's a 0, and that is a 0. That means in this case, we would need 3 electrons. Gives me a -3, and a +3 is 0 on both sides in this case. Any questions so far? All right, I'm just going to kind of clean up some of my scribble here. Get rid of some of that there. Get rid of that too. Okay, now that we did that, we're ready to add these together. Once again, we do need to make sure we have the same number of electrons in each half reaction And in this particular case, we do not. We are going to have to multiply actually both of them by a common number. We got 2 electrons in the first one, 3 in the second. 3 times 2 is 6, so times the top guy by 3, bottom one by 2. We're timesing everybody by those numbers. So rewriting it gives me 6I minus goes to 3I2 plus 6 electrons. Distributing the 2 on the bottom there, 6 electrons plus 8 H pluses plus 2 MnO4 minus, 2 MnO2 and 4 waters. Adding these guys together, electrons should completely cancel, which they do. We also know we added it to the correct sides, oxidation to the right, reduction to the left there. That I think might be it in terms of canceling. That's going to leave me 8 H pluses plus 2 MnO4 minus plus 6I minus goes to 3I2 plus 2 MnO2 and 4 waters. Technically speaking, if I want to balance in acidic conditions, I should put a box on it and I'm done at this point. But we are looking for basic conditions. So we're going to now turn this into basic by adding an equal number of OH minuses to both sides, equal to the H pluses we have, which in this case would be 8 OH minuses to both sides. Again, the side here that has H plus and OH minus, they will combine to make 8 waters, which typically can be reduced down. And if I do that, that will leave me 4 waters plus 2 MnO4 minus plus 6I minus 3I2, 2 MnO2, and 8 OH minuses. And again, we should be balanced in basic conditions. We see that with the OH minus being present. Overall on the left there, we got 8 hydrogens and 8 on the right. 4 and 8, 12 oxygens on the left. 4 and 8 is 12 on the right. 6 I's on the left, 6 on the left, right. 2 MNs on both sides. Overall charge here, -8. Overall charge, -8. So we are balanced again in both ways, both elements and charge on each side. Any questions on any of those steps there? All right, we will lay it up.